Hello students, in this video let me explain what are equipotential surfaces and also how to draw an equipotential surface for a various charge configurations. Now first let me take the definition of an equipotential surface. An equipotential surface is a surface with constant value of potential at all the points on it. I will read it again. An equipotential surface is a surface with constant value of potential or same value of potential at all the points on it. That's the definition of equipotential surface. Now, let me write an equation for potential due to a point charge. The equation is V is equal to 1 by 4 pi epsilon naught into Q divided by R. So, we know that this 1 by 4 pi epsilon naught is a proportional constant and the value of this potential V depends only on the magnitude of charge and the distance of a point from that charge. Suppose if I say the magnitude of charge is fixed, so then this potential, the value of potential depends only on the distance of that point from the charge, that is on R. Suppose if we say the value of R is constant, then we can say that the value of V also remains constant. Correct? So if the value of R remains constant or same, then the V should be constant. So if I consider a charge is placed at this point and let me draw the two circles around it. See, these are the two circles around this charge. The situation is that the charge is placed at the center and these are the two concentric circles around it. Now first consider this circle. If you stand anywhere at the edge of a circle, from the center to any point, the distance will remain same. Now, if the charge is placed at the center and we are calculating the potential on the surface of this circle, the value of potential remains same because you know that radius remains constant in a circle. So from this point charge to any point on the circle, the distance is same. Since the distance is same, the value of potential also remains constant. That is why we can consider this surface as an equipotential surface. Next, if I write another circle here, this is another circle, but the radius is different from this circle. But if I consider any point along this circle, the value of potential remains same because the distance from the charge to any point on the circle is same. So that this is also an equipotential surface. Then what are equipotential surfaces? The thing is that the potential value should remain constant throughout its surface. Then we can call them as equipotential surfaces. Now, a very important result is that work done to move any charge on an equipotential surface is 0, that is W is equal to 0. So consider this equipotential surface. Let me assume the 2 points from here to here, that is on the circumference of a circle only. So just now we told you that the potential remains constant throughout the surface, hence the difference in potential between any 2 points is 0. Since the potential is remaining constant at any 2 points, the value of potential is same. Therefore, the difference in potential is 0. Potential difference is 0. Now, if I want to move a charge from this point to this point, where the potentials are same, no need to do any work because the potential is same or potential difference is 0. We need not to do any work to move a charge. That is why the work done to move any charge on an equipotential surface is 0. So you may get a question on this topic. What is the work done to move any charge on an equipotential surface? So your answer should be 0. Okay. Now let us draw some equipotential surfaces for different charge configurations. For first one, if this is a positive charge, a single point charge, for a single point charge, the equipotential surfaces are concentric circles. I have already explained you that. Next, for an equipotential surface for a dipole, if you consider a pair of equal and opposite charges, negative charge and positive charge, an equipotential surfaces will look like this. Next, equipotential surface for a pair of equal charges. If both are positive charges, then the equipotential surface will look like this. Now the fourth one, very importantly, equipotential surface for a uniform electric field. How to represent an uniform electric field? An uniform electric field is represented by a parallel straight lines. So an equipotential surface for an uniform electric field is a plane surface drawn perpendicular to the electric field. Because if you look at this one, these are the directions of electric field lines for a single point charge or for a positive charge. This is always perpendicular to the tangent of a circle. So at any point, an electric field is perpendicular to the equipotential surface. That is why in this diagram, if we write an uniform electric field by the parallel straight lines, a plane surface drawn perpendicular to the electric field makes an equipotential surface. You can observe here also. So there are 3 equipotential surfaces here for an uniform electric field. So the plane surfaces drawn perpendicular to the electric field will be a equipotential surfaces. Next. Yes, this is very important derivation or an important result. We have to derive the relationship between electric field and electrostatic potential, or we should show the electric field E is equal to minus of dV by dx. So this question will be asked for 3 marks in your examination, or an expression may be asked for 1 mark. So observe carefully. First, if you observe the diagram, here there are 2 equipotential surfaces. A is one equipotential surface, and below that we have one more equipotential surface, that is B. The value of potential at the surface A is V plus delta V, and the value of potential at the lower surface will be V. Now the field direction, the electric field is directed from B to A, so we have to bring or we have to move a charge from A to B against this electric field. So I have an unit positive charge, so that unit positive charge is moved from A to B against this electric field. So we know that to move any charge against the electric field, work has to be done. So the work done is given by, work done is equal to charge multiplied by potential difference. That is the equation for work done. Work done to move any charge Q is given by W is equal to Q into V, that is charge into potential difference. Now since we are moving a unit positive charge here, so this Q will be 1 in magnitude. So we are moving a charge from A to B, that is a unit positive charge. Actually this is A to B, you have to make a changes. A to B, this is not B to A, this is from A to B. Now you are moving a unit positive charge from A to B, therefore the value of this Q will be 1, and this is V, potential difference. The potential difference between the two surfaces is V minus V plus dV. The difference in potential is V minus V plus dV. V is the final potential, that is potential on the surface B, and V plus dV is the potential on the surface A. So we are moving from A to B, so final potential V minus initial potential V plus dV. So V minus V plus dV, so you can cancel V and minus V here, so that the work done dW will be equal to minus of dV. Now We know the definition of work done. Work done is given by force into displacement. The work done is force into displacement. But the force experienced by a unit positive charge is called electric field. Therefore, the force is replaced by electric field E dot. The displacement is dx. So from A to B, the displacement is dx. Now I know that this dw is equal to minus dv from this equation. So that let us substitute this minus dv here. So minus dv is equal to E dot dx. And finally, if I rearrange this, we get E is equal to minus of dv by dx. So this is the relationship between electric field and potential. So this equation is read as electric field is equal to negative potential gradient. So we have minus dv by dx. So this dv by dx is nothing but a potential gradient. So we have to say this electric field as electric field is a negative potential gradient. And this derivation will be asked for 3 marks in your examination, or you may get a 1 mark question also. Like write the relationship between electric field and potential. So you can write the relation as E is equal to minus dv by dx, so that electric field is a negative potential gradient.